In this video, we are going to begin to review for quiz 4 by talking about Bayes probability questions versus Bernoulli trials probability questions. So overall, our goals for this section are just to do some practice problems to help review for the quiz. Okay, so let's get into this specific topic of Bayes versus Bernoulli. So recall that a Bayes probability problem is one in which it is easy to compute one conditional probability, like the probability of A, given that B occurs, but we want to find the reverse conditional probability. We want to find the probability of B given that A occurs. And a Bernoulli probability problem is one in which we repeat an experiment. So we are going to repeat an experiment, usually several times, and there are two outcomes in each stage. So two outcomes in each stage. So for example, so I'm going to write e.g. for example. Suppose we did 10 coin flips. So we are repeating an experiment, flipping the coin 10 times. And we were interested in something like, well, let's say I wanted to find the probability of getting 6 heads. For each coin flip, there's two outcomes. Either I flip heads or I flip tails. And the fact that I'm repeating that thing several times makes this a Bernoulli probability problem. So when we do have a Bernoulli situation, recall that the probability of having k successes in n trials, one of the things I need to do to find this probability is count the number of ways to have k successes in n trials. And then I also need to multiply this by the probability of each outcome. Okay, and we've seen before that the number of ways that we could have k successes in n trials is n choose k. And the probability of each outcome, well, each of the successes, let me label this. So before I write down the probability of each outcome, let me say where I'm going to let P be the probability of a success, and I'll let Q be the probability of a failure. So it's convention to label the two outcomes in a Bernoulli trial as a success and a failure. So if I have k successes, then I'm going to need to multiply that probability, p times p times p, k times. So that'll give me p to the k power. And then I'll need to do the same thing for the number of failures. So we'll have q to the however many failures we have. So if we have n trials and k successes, that means we have n minus k failures. And that gives me q to the n minus k. Okay, so let's highlight this. This is a key formula for our section on Bernoulli trials and doing probability questions involving situations where we had Bernoulli trials. All right, so let's look at an example. So this question says, for each of the following, determine whether it is a Bayes or a Bernoulli problem. And if it's Bernoulli, then solve it. So that means if it's a Bayes problem, I don't want us to solve it. Main reason for that is we've done a lot more examples of Bayes problems over the course of a few sections. Okay, so for part A, it says O'Reilly Auto Parts estimates that 1 in 5 cars needs to replace their car tires. Car owners who need a replacement will get an oil check 70% of the time, whereas owners who don't need a replacement will get an oil check 55% of the time. A randomly selected customer got an oil check. What is the probability that they also needed a tire replacement? So I want to begin by having you pause the video for 1 minute just to think about, well, is this a Bayes question or a Bernoulli problem? 4, 3, 2, 1, pause it and see if you can answer that question. If you know the answer, then start to work it out, but only for a minute or so. Alrighty, so hopefully you did that. Hopefully you paused it and tried this for about a minute. So the key for this question is to recognize that there are two different stages. There's one stage where we talk about, well, does this car need a tire replacement or does it not need a tire replacement? And the next stage involves two different outcomes about whether they get an oil check or whether they don't get an oil check. So this is suggesting that this is a Bayes question. Even though there are two outcomes in each stage, we're not just repeating the same thing again and again and again. Like up above, if we had coin flips, if I flip a coin again and again and again, I'm repeating the same experiment, the same stages again and again and again. But here, that's not happening. One of the stages involves car tires being replaced or not, needing to be replaced or not, and the other stage involves whether they get an oil check or not. Okay, so I'm gonna say I'm gonna leave this for you to try. I'm actually not gonna work it out in the video. All right, so let's look at the next part of this example. Part B is another scenario. It says, O'Reilly Auto Parts estimates that 1 in 5 cars needs to replace their car tires. On a randomly chosen day, 20 cars visit their shop. Assuming each car is independent, what is the probability that exactly 4 cars need a tire replacement? So I want to begin by having you pause the video for just a minute again to think about, is this a Bayes or a Bernoulli question? 4, 3, 2, 1, pause it and try to think about that for about a minute. Alrighty, so let's talk about that together. So in this question, there are two outcomes for each car. And those outcomes are either they need to replace their tires, or the other outcome is they don't need to replace their tires. And we're asking that question for each car that visits O'Reilly Auto Parts. So we're repeating this experiment, this check for each car, and that makes this a Bernoulli question. All right, so I need to find the probability that exactly 4 of these cars need a tire replacement. I'm just going to write 4 need a replacement. Okay, so using our idea for Bernoulli probabilities, I need to first count the number of ways to choose 4 out of 20 cars who need a replacement, and then multiply that by the probability of each outcome. All right, so the number of ways to choose 4 out of 20 cars, that is going to be 20 choose 4. And then based off of what the question says, the outcomes are need to replace tires and don't need to replace tires. So from need to replace, I'm going to consider this as my success here because my question is asking about the probability that some number of cars need a replacement. So I'm going to denote this with the letter P. So it says 1 in 5 cars need to replace their tires. So P is 1/5. And that will make don't needing to replace their tires. I'm going to label this probability with Q. So Q would be 4/5. All right, so now I'm ready to fill these in. So I have to multiply 20 choose 4 times P, 1/5, raised to the number of successes. In this case, there's 4 successes. There's 4 cars that need their tires replaced. And then I multiply that by 4/5. That's the probability that a car does not need to get their tires replaced. And then I multiply that by the number of cars that don't need to get their tires replaced, which in this case is 16, because there's 20 total cars and 4 need a replacement. All right, so using a calculator to work this out, I'm going to round this to 3 decimal places. This is about 0.218, and that is our answer. All right, so let's go to the next question. So that was part B. C asks, well, in the scenario from part B, what is the probability that less than 4 cars need a tire replacement? Okay, so for this one, again, I'm going to ask you to pause the video to get it started. Pause it for about 3 minutes to try this question. 4, 3, 2, 1. Pause it and try this one for about 3 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 3 minutes. Let's talk about it together. So this question is asking, what is the probability that less than 4 cars need a tire replacement? So if it's less than 4 cars that need a tire replacement, that could mean either 0 cars or 1 car or 2 cars or 3 cars that need to get their tires replaced. So I'm going to add up those probabilities. So it's the probability that 0 cars need a replacement plus the probability that 1 car needs one, plus the probability that 2 cars need it, and then finally plus the probability that 3 cars need it. Okay, so let's work out each of these. So each of these I can determine using my formula for Bernoulli probabilities. Okay, so for 0 cars, I would have to do 20 choose 0, and then multiply that by the probability of a success, 1/5. That's the probability that a car needs to get its tires replaced. And in this case, I want 0 cars to get their tires replaced, so the exponent is going to be 0. Okay, and then multiply that by 4/5. That's the probability that a car doesn't need to get their tires replaced. And there's going to be 20 cars that don't need to get their tires replaced here. All right, so let's keep going in this way. For the probability of 1 car, let's see, there's going to be 20 choose 1 ways to choose which one of those 20 cars needs the replacement. And then I multiply that by 1/5 to there's 1 car that will need a replacement. And then multiply that by 4/5 to the number of cars that don't need a replacement, which is going to be 19. Okay, and I'm going to shift that over a little bit. For these last 2 probabilities, I'm going to do these a little bit more quickly. For the probability of 2 cars, there's going to be 20 choose 2 ways to pick which 2 of the 20 cars need a replacement. Multiply that by 1/5 to the 2, because there's 2 cars that need that replacement. And then we multiply that by 4/5 to the 18, because there's 18 cars that won't need a replacement here. All right, and then plus, for 3 cars, I need 20 choose 3 first, and then multiply that by 1/5 to there's going to be 3 cars that need a replacement, so 3 in the exponent. And then 4/5 to the number of cars that don't need a replacement, which is 17. Alrighty, so we have all of this. Plugging this into a calculator, I am going to round this to 3 decimal places, and we get 0.411. So that is our answer. Okay, so let's do one more of these. Okay, so part D asks, in the scenario in part B, what is the probability that more than 4 cars need a tire replacement? Okay, so, and I think I forgot to say something. In part C, we kind of assumed this, but part C was a Bernoulli problem. This was a Bernoulli problem. Okay, so for part D, I want to begin by having you all pause the video and try this. So pause it for just 2 minutes to try this one. 4, 3, 2, 1. Pause it and try it for 2 minutes. Alrighty, so hopefully you did that. Hopefully paused it and tried it for about 2 minutes. So this question is also going to be a Bernoulli problem. So it's similar to C in that we're talking about a range of values. This one is more than 4 cars. Part C was less than 4 cars. So if I want the probability of more than 4 cars, well, that could be the probability of 5 cars plus the probability of 6 cars plus the probability of 7 cars plus plus up until the probability of 20 cars. That all 20 need a tire replacement. But that is a bunch of values, a bunch of probabilities. So doing it like this is definitely looking tedious. And often, if counting something directly in this way is tedious, we think to try the complement. Like, let me give myself some more room here. We're going to try the complement. And to help us see what the complement is, I'm going to draw a Venn diagram. So let's make a rectangle for our universal set S. And S is just going to represent all the possibilities. All the different numbers of cars that we could have who need a tire replacement. And within that, I'm going to have my set A that we care about. And in this question, we want greater than 4 cars to need a tire replacement. Okay, so then I can form the complement, a complement. What's the complement of greater than 4 cars needing one? It would be less than or equal to 4 cars needing a tire replacement. Let me just write tire replaced. Okay, so one thing to be super careful about is that the complement of greater than 4 is not just less than 4. It's less than or equal to 4. Okay, so now that we have this diagram, we are ready to compute this probability using complements. If I want the probability of greater than 4 cars needing a replacement, I'm going to find the probability of the whole rectangle, the probability of my sample space, minus the probability of that complement set of less than or equal to 4 cars. Okay, and the probability of the whole sample space is always going to be 1, because that is every single outcome included. Okay, so we're going to have 1 minus, and now I need the probability of less than or equal to 4 cars. And that, I can just tackle it directly. This would be the probability of 0 cars plus the probability of 1 car needing a replacement plus probability of 2 cars needing a tire replacement plus the probability of 3 cars plus the probability of 4 cars. Okay, and we've worked out the different portions of this bracket in the earlier parts of this question. So 0 cars up until 3 cars, we did this. We did this in C. So we're happy about that. And then for the probability of 4 cars, well, we did that in B. So we're happy about that. Okay, so if we use the values that we got in part C and in part B to plug into the bracket, we will end up getting that this is approximately 0.370 if I round it to 3 decimal places. And that is our answer. So in the next video, we are going to continue to review for quiz 4 by looking at random variables.